So, welcome everybody to today's math class, the last math class of this year. To start this class, I have a quick warm-up exercise for you. So here's two series, and I'd like you to see if those converge, and if so, please also determine the limit if you can. I'll set up two tweetbacks so that you can submit your answer on those. Right, just a quick show of hands. Who's done with the first warm-up problem? Who's done with both the first and the second? And who needs some more time? All right, maybe I'll give you a couple more minutes. For those who are done already, I'll also open 2 more quizzes where you can assess the difficulty of those 2 problems. And maybe let's take 3 more minutes until 1:30. All right, 30 more seconds. All right, so let's first take a look at your difficulty assessment. So that was your answer for question 1. Most of you found that one pretty difficult. And here's your answer for question 2. That was slightly easier. You noted I used both of these in past exams. The first one is from 2020, the second one is from 2019. And indeed, I would say question 1 was one of the harder questions of that exam, while I would expect question 2 to be more on the easier side. And of course, it also reflects in your answers. So maybe let's first have a look at question 2, the easier one. Does the series converge? Most of you think it does converge, and the limit is 9, and that is the correct answer. Maybe let me quickly show you how to do that. Let's start with question 2 then. So once again, the problem statement specifically asks for the limit if the series converges. And that means you'll have to find one of those series that you know and reformulate it in a way such that you can compute the limit. And in this case, when we have 2 to the power of 3n over 3 to the power of 2n, so it's something to the power of n. And that means I would suspect there's maybe a geometric series behind this. So that would be my first try, reformulate this as a geometric series. And that is indeed what you can do. If you just realize that 2 to the power of 3n is the same thing as 2 to the power of 3 to the power of n. And the same thing is true for this here. So 3 to the power of 2n is the same as 3 to the power of 2 to the power of n. And that means you can write this as 8 over 9 to the power of n. And that's your classical geometric series. Which means this factor here, that's our q, that is less than 1, so it does converge, and the limit is given by 1 over 1 minus that factor. So 1 over 1 minus 8 over 9, and that is 1 over 9, and that is, of course, 9. Right, so that's how you get the answer of this one. All right, questions about that? Before we turn to the more complicated one. So for problem 1 then, let's take a look at your answers here. Most of you think this series does not converge, and then there's 2 runner-ups at 8% each that say the series converges and the limit is 0. Should be easy to exclude that. And then some think it converges and the limit is e to the power of 3 minus 1. And while not a lot of you recognize that, this is indeed the correct answer. Let me tell you why. So I'd say this is mostly problematic because it might not be immediate to recognize the correct series to use here. But to give you a brief idea of what could help here, roughly this is something like something to the power of n over something n factorial. And that should remind you of a series that looks like this. You hopefully have seen that. That is Euler's series. That does converge for every x, and the limit is e to the power of x. And that's exactly what we'll be using here. We just need to reformulate that slightly. And the first thing that we do is we take out that 3 to the power of n here. Right, that appears here and here. We can factor that out. And then we get n plus 1 over n plus 1 factorial. And now one of these n plus 1 factors, this factor and the last of this factorial, those cancel out. So we are left with 3 to the power of n over n factorial. Right? Remember this n plus 1 factorial, that's the same thing as n factorial times n plus 1. So we can cancel out that n plus 1 factor. And now we're almost here. Right? This is exactly this form here. X in this case is that number 3. The only difference is this starts from 1 and this starts from 0. So we have to add a small correction factor to take that into account. So let's say if we start this from 0 instead of from 1, the The factor that corresponds to n equals 0 is 3 to the power of 0 over 0 factorial. 0 factorial is 1. 3 to the power of 0 is also 1. So that factor is 1. And that means we added a factor of 1, so we'll have to subtract that factor to make up for that error. Okay, so that's the same thing. And now we can just use this formula for Euler's series. Right, see above. So this first sum here is e to the power of 3, and of course the minus 1 just stays there. Right, so that's a same principle, same idea, basically. Just need to put in a little more work to get rid of that disturbing factor here. And of course that, you need to have that series here in mind to be able to recognize that. So if you have not remembered Euler's series, you should take note of that. It will appear again in a later chapter in a very important context, actually. All right, questions about that? Good, otherwise, I'd say maybe let's take a quick look at the homework before we go on. Homework 1, we've talked about that already. Homework 2, so you should now be able to solve homework 2 without major problems, I hope. Where is my mouse pointer? Here it is. So question, did you have any problems with homework 2? Should we talk about one of those problems? Yes. A. All right, maybe let's have a quick look at that before we move on. So H10.2 part A. Just put my sheets in order here. So let me just copy that once. So we have the sum from 0 to infinity, 1 over 2 to the power of k plus 1 plus minus 1 to the power of k over 3 to the power of k. All right. So what we have here is basically a combination of some of the facts that we've been looking at so far. What would you say? Will this converge or not? Quick show of hands. Who thinks it will converge? Who doesn't? And what type of series could this be? Geometric series? Let's give that a try, shall we? So, geometric series, we have this 1 over 2 to the power of k plus 1. We have this 1 over 3 to the power of k plus 1. The only complicating factor is this minus 1 here. That doesn't seem very nice. But maybe that is not problematic after all. Let's take a quick look. So if we were just to split that up, for example, we could write that as 1 over 2 to the power of k plus 1 from 0 to infinity plus minus 1, let's maybe write it that way, minus 1/3 to the power of k from 0 to infinity. Now do these converge? And why? Any opinion? Yes. So you say they converge and we can just apply the formula. After changing the file on the first one, all right? So we need to do that first. So the problem here is we have a k plus 1 instead of a k. So what this means is basically we're starting our summation from 1, right? If we use k equals 0, then we have 1/2 to the power of 1. So this is basically 1/2 plus 1/2 squared plus and so on, right? And for the geometric series, we'd have to start with 1/2 to the power of 0, and that one is missing here. So what that means is this is the same thing as this here, 1/2 to the power of k, but in this case we included that to the power of 0, so we have to subtract that to make up for that. Right, and now we have pure geometric series here. And in this case, we'll minus 1/3 to the power of k. That does start at 0 as it's supposed to be, so no problems here. Right, and now we can just use the formula. That's 1/1 minus 1/2 here, minus 1, sorry, plus 1/1 minus 1/3. Right, and then you just have to do the computations and get the result. Guess I can leave the rest here. So basically that's just 2 geometric series rolled into 1. But of course, if both of those converge, you can split that sum up. If one of those didn't converge, you could not do that. But as both as single series do converge, there's no problem in doing that. All right. Any troubles with B? I hope not. So basically, you should be able to recognize that B boils down to one of those telescopic sums. So if you just write down a few numbers, you'll recognize what happens here. And then you'll be able to compute the limit, hopefully. Okay. If there's no more questions about that, yep. Yeah, sure, you could do that as well. So the question is, instead of doing this reformulation here, as I did, you could also, let me maybe write that down somewhere. You could also say, I'm going to factor out 1/2 here and write that in this way. So it's 1/2 times this sum and then just to the power of k. Yeah, that's fine. Should hopefully get you the same result. Any more questions? Otherwise, let's move on to the last topic of this week. And that is absolute convergence and convergence criteria. And up to this point, what we have done is we have considered series where we can't explicitly determine the limit. That might, of course, not always be the case. There might be series where we might be able to prove that they converge in some way, but still we might not be able to easily obtain the limit of those series. We've seen a few examples of sequences of that kind already. For all kinds of sequences, we have this one criterion that says if the sequence is monotone and bounded, then it has a limit, but the theorem doesn't give us a way to recover that limit. So we might be able to prove a sequence or even a series converges by that theorem, but we might not get the limit from that immediately. And for series, of course, you can also apply that criterion, but then there is also a few other criteria that might be easier to apply that will give you convergence or divergence, maybe, but might not get the limit of that series. And that's what we talk about here in this chapter, about convergence criteria. Now, the first fact to mention is that these criteria that we talk about here apply to absolutely convergent series. And the series is called absolutely convergent if not only the series itself converges, but even the series of the absolute values converges. If you replace the summands by the absolute values, then that still converges, right? Of course, that's even harder than simple convergence that series. Here you could have something like alternating signs, for example, and maybe some of those factors cancel each other out, and that's why the series will converge. But if you take absolute values, the series might not converge anymore. For the two criteria in this section here, they will ensure that the series even converges absolutely. So even if you replace all the signs by pluses, it will still converge. And of course, that means the series without absolute values also converges, right? That could be smaller than this one, but it couldn't be larger. All right. So here's the criteria that we have here. This first, the comparison test, we've already applied that one, so I'm not going to talk about that for long. Basically, the idea is if you are able to bound the series, so if each of those elements is bounded by some other element and the series over those other elements converges, then of course the original series is smaller than that, so it also converges. What we did is we applied that in the reverse direction, and of course that also works if you have a series that is divergent and your series is even larger than that, of course this will also diverge. Remember, we used that to prove that series that look like the harmonic series diverge by comparing them to the original harmonic series. All right, so that's often used in that reverse direction as well. What is more important are those two tests here, the ratio test and the root test. What you do for those is, first take a look at the ratio test. You look at expressions of that form here. So you take two consecutive summands in that series for a general index, and you compute the ratio of ak plus 1 over ak. Take the absolute value of that, and then see if this is strictly less than 1. And that does not have to hold for all possible indices, but it has to hold eventually. So that means you can exclude a number of elements at the beginning if you want that don't really matter for convergence, but there needs to be some index such that from this point on this will always hold. In other words, and that's what you usually do, most often you'll just take a look not at all of these expressions, but instead at the limit of these expressions. And that does just that. So the question is, how does this term behave in the long term if I increase my k indefinitely? Right? So I'm not looking at possible exceptions at the beginning. I don't care about those. I'm just interested in the long-term statement here. That means I'm taking the limit, and if that limit is strictly less than 1, that means my series converges absolutely. If my limit is strictly greater than 1, that means my series so the absolute series diverges, does not converge. Problematic case is if I get a limit of equal to 1, because then that test doesn't tell me anything useful. It could converge, it could diverge, anything can happen. I'm not smarter than before, right? So that was all useless. Hopefully that won't happen. If you get one of those two cases, the test worked and gave you an answer. And then there's second test, the root test, works similarly. In this case, you take the kth root of the absolute value of AK. Look at that expression. And again, the question is, will this eventually be strictly less than 1 for large enough K? And again, you usually consider the limit to answer that question. And if you ask if that limit is less than 1, strictly less than 1, then the series converges absolutely. If it's strictly greater than 1, then this series diverges. And if it's equal to 1, who knows? The test just didn't work, right? Generally speaking, the root test is the stronger of those two. So you can prove in a pretty abstract way that whenever the ratio test works, the root test will also work, but there are cases where the root test gives you an answer and the ratio test doesn't. However, the ratio test is usually much easier to apply, right? Taking kth roots is not that easy, and you'd like to avoid that if possible. Sometimes it's not possible. But if you can, I'd try the ratio test first. And only if that doesn't work, and if you have a feeling that the root test might give you a useful answer, then I go for that. All right, a couple of examples here. So just very quick, this here, the series of 2 to the power of k over k factorial. Of course, basically, you know that this is Euler's series, so this will, of course, converge. But if you want to apply the ratio test to this one, and something that contains factorials, is usually a good candidate for the ratio test, right? Because if you consider ak plus 1 and ak, you have a k plus 1 factorial in one and a k factorial in the other. And that means most of that expression cancels out. Yeah? You're just left with this k plus 1 factor. Those cancel out. So that makes factorials a whole lot easier. And of course, also those powers of k, right? You usually have something to the power of k plus 1 over something to the power of k, so most of that will also cancel out. In this case, it's the 2 to the k. Okay, so you get something like 2 over k plus 1. And of course, if k goes to infinity, then this tends to 0, so that's definitely smaller than 1. So this does converge. Right? And you can also see this does not depend on the 2 at all. I could have written anything instead of that 2. It will always converge. All right, so that's an example for the ratio test. Another quick example for the root test. Often if you have an expression that has a power of k and a power of k, and no other expression, so that it's easy to get the kth root of that, then the root test might be a good idea. And that's what's happening in this case here. Yeah, so if I take the kth root of this one, I'm just getting rid of this powers of k here, and I get that expression. And of course, it's easy to see what happens here, right? So this only depends on whether k is even or odd. And in both cases, the result is less than 1. And then, of course, the limit is also less than 1. So this also converges absolutely by the root test. All right, and one final test before we go on with more examples, the Leibniz test. That is a criterion for series that might not converge absolutely, so where the sign is actually important and that do alternate. So what we have here is a series of that type, some ak, and the signs alternate. So I have something like minus 1 to the power of k times some actual term ak. And what the test says is if those ak are a decreasing sequence that converges to 0, and of course that implies that the ak are actually non-negative, otherwise they couldn't decrease and converge to 0. Right, maybe I should write that down as well. So this implies that the AKs are greater or equal to 0, at least from some point on. Yeah, in the beginning, some of those AKs might even be negative, we don't care. But in the long term, they become positive. And if that is fulfilled, so if the AKs form a decreasing sequence that has a limit of 0, then the Leibniz test says this series converges. Not necessarily absolutely, but with the sign alternation, it does converge. Right? And of course, again, if you have a sequence that has this alternating sign in here, that's usually a sign to look up for the Leibniz test. Okay, quick example, classic example is the alternating harmonic series. So you do know that the harmonic series, so without this -1 over k, that does not converge. But if I add that here, of course, this sequence here, 1 over k, that is decreasing and converges to 0. And that means with the Leibniz test, we immediately get that this series here is indeed converging. Okay, so the Leibniz test tells us the alternating harmonic series does converge. Again, it doesn't give us a limit, so we only know it does converge. We don't get the limit, but at least we get that. Same thing for the ratio and the root test. We don't get a limit from those, we just know the series does converge. If you want a limit, we'll have to resort to some other means. All right, questions before we look at some examples? Maybe let's take some examples first and then see if any questions pop up. Let's see. Maybe let's start with those two. So first example, series from 1 to infinity, 2 to the power of n factorial to the power of 3 divided by 3n factorial. And I'll also give you a second example right away. Series from 1 to infinity over 1 minus n plus 2 over 4n plus 2 to the power of n. And now you should probably guess, well, this series here, that does look a little, maybe a little too complicated to figure out the actual limit, but it shouldn't be hard to get to obtain whether it converges or not. It's all positive anyway, so convergence is the same as absolute convergence in this case. And there's only this 1 power of n, but there are factorials in here, so probably you want to try the ratio test on that one. At least that would be my first idea here. And for the second one, you recognize this has the form something to the power of n. So taken in nth root might simplify that considerably. And that means the first thing I'd try here would actually be the root test. All right, so give it a try, and then we'll see what you get. for those who are done, I've started to tweet back questions to see if the series converges or not. Quick show of hands. Who's done with the first example? Who's done with both the first and the second one? And who needs some more time? Quite a few, so let's take 2 more minutes or so. Question? So you mean, does it matter what the indices are? If they start from 0 or 1 or something? Doesn't really matter. So we only ask for whether it does converge or not. Of course, if you exclude some of those summons, so in this case here, for example, we start from 1, we could as well start from 0, right? Wouldn't really matter. If that converges, then of course the one that starts at 0 will also converge and vice versa. The limit will change, but the property of whether it converges or not, a few summons don't really matter for that. Yeah, so that doesn't make a difference for those tests. All right, 1 more minute, and then we'll quickly discuss your findings. All right, so here's your answer for the first example problem. Most of you think the series does converge, and as often, most of you are right. Let's take a quick look at how to apply the root test here, where we discussed that, the ratio test, where we discussed that. This is probably the ratio test we want to apply. For the ratio test, remember, we are looking at those summons here, right? So those are the ANs. This is the AN that we're looking at. And for the ratio test, we will consider the fraction AN plus 1 over AN. And if necessary, we'll take the absolute value of that. In this case, it's all positive anyway, so we can forget about this absolute value. So let's see, AN plus 1, that is 2n plus 1 times n plus 1 factorial to the power of 3 over 3 n plus 1 factorial. And we need to divide that by an. So in other words, we multiply by 1 over an. And 1 over an is 3n factorial. And divided by 2 to the power of n times n factorial to the power of 3. All right. So what's happening here? First thing we notice that should be easy here. We have this 2 to the power of n plus 1 and 2 to the power of n. So of course that cancels out, and we're left with the 2 in the numerator. So that reduces to just 2. Now let's take a look at those factorials. That's not so nice, unfortunately. First thing we have here is we have this n plus 1 factorial to the power of 3. And we have this n factorial to the power of 3. That basically means we have n plus 1 factorial times n plus 1 factorial times n plus 1 factorial, and the denominator n factorial times n factorial times n factorial. So of course for each of those, we can cancel out most of that. Remember that n plus 1 factorial is n times n factorial times n plus 1. Right, so if you divide that by n factorial, this factor here cancels out, and we're left with just n plus 1. And we just do this 3 times here. Before I do that, let me maybe just add the rest before I write that down. We also have 3n factorial, just copy that. And 3n plus 1 factorial. Now I already said for those here, this n factorial cancels out for all 3 of those factors, so we're left with just n plus 1 3 times, so to the power of 3. Right, and then we have this 3n factorial. And here we have 3n plus 3 factorial. Right, so this is this here. Right, just multiply the 3. It's 3n plus 3 factorial. All right, and now what we do is just copy those first parts. 3n factorial, and now of course this 3n plus 3 factorial, that's the same thing as 3n factorial times 3n plus 1 times 3n plus 2 times 3n plus 3, right? Same idea as here, but I'm not going for plus 1, instead I'm going for plus 3. So that means I have 3 more factors. And again, this factor here cancels out. So what we get now is 2 n plus 1. Let me just write that out. N plus 1, n plus 1, n plus 1 over 3n plus 1, 3n plus 2, and 3n plus 3. And now we are in a situation where we should be able to determine the limit as n goes to infinity. One quick remark, if you ever find yourself in a situation like that, the worst you can do is multiply this out. You'll just make a lot of mistakes and we'll all be wrong in the end. Don't do that. I've seen that too many times in exams. Right? So if you can, avoid this multiplying things out at any cost. It's usually always better to have that factored out already. I've seen lots of people multiply this out, then factor it out again and make mistakes. Don't. All right, so how do we compute the limit? Here in the numerator we have n times n times n, so basically that's an n to the third plus something polynomial. Here we have 3n, 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 so again that's an n to the third plus something polynomial. So the highest degree is n to the power of 3, and that means, usual trick, we just divide everything by n to the power of 3. And now what I do is, I'll divide that factor, so I have these 3 factors here, and dividing everything by n to the power of 3, I can just use 1n here, 1n here, 1n here. And same thing here, right? It's a product, so I can shift that around as I want. Okay, so that means what I get here is 1 plus 1 over n. I divided this expression by n. And I do the same thing for these expressions, and of course I get the same result. 1 plus 1 over n, 1 plus 1 over n. And in the denominator, I'm doing the same thing. I'll divide this by n, I'll divide this by n, I'll divide this by n. So here I get 3 plus 1 over n, 3 plus 2 over n, and 3 plus 3 over n. And now as n goes to infinity, well, all of these here go to 1. All of these here go to 3. And that means I get 2 times 1 times 1 times 1 over 3 times 3 times 3. And obviously that is less than 1. Yeah, so the limit is strictly less than 1. And that means this series converges, convergence. All right, so that's usually how you apply the ratio test. Just write it down first. Be sure to take the absolute value if necessary. And then try to simplify your expression such that you can cancel out the complicated terms until you're left with an easy enough expression to compute the limit. All right, questions about this one? And let's briefly take a look at the second example problem. And then I'd like to address some of the questions that have piled up on TweetBack. So for the second problem, this is your answer. So most of you again found the series is convergent. Let's take a look at that series once again. So this here, just copy that. That was a series here. And of course, if you have done your homework, you recognize this is exactly 1.3a, I think, right? Yeah, exactly this one here, just with an n instead of a k. So let's quickly discuss that one. I already said in this case, I go for the root test simply because that significantly simplifies this thing here. So we do that. Root test. And root test means we have to use the nth root of the absolute value of an. And again, an is this expression here. This is our an. This second part here is less than 1, so 1 minus that will always be positive, so no need to take this absolute value into account. It will all be positive anyway. So that means we can simply apply the nth root directly. And let me just write that down once more. So we want the nth root of 1 minus n plus 2 over 4n plus 2 to the power of n. So of course, as it's all positive, this nth root is 1 minus n plus 2 over 4n plus 2. And then we can again apply the usual trick to compute the limit. In this case, for this fraction, the highest power that appears is just n. So we just divide everything by n. And we get 1 minus 1 plus 2 over n. And 4 plus 2 over n. And that means as n goes to infinity, we get 1 minus 1 over 4, right, as those expressions just go to 0, so we're left with the constants 1 and 4. And well, 1 minus 1 over 4 is 3 over 4, so that is strictly less than 1. And again, that means the series converges, convergence, even absolutely. Okay, so that's how you could apply the root test. And again, the ratio test is usually easier. I would only go for the root test if either ratio test doesn't work and I don't see a good alternative, or if it's immediately clear that taking the nth root will simplify things, like in expressions that have this to the power of n outside. Okay, questions about this one? Yes. What do you mean by what form? Exactly. So it doesn't really matter what functions are inside there. If there's a root, a square, a factorial, to the power of something, whatever, you can apply the tests no matter what is inside those summons. That is correct. They might not work, or you might not get a good result because you might not be able to compute the limit if it's all too complex, but you can try. Yes. So if you get a limit of 1, test is inconclusive. So you basically wasted your time with that. Sorry? So if you get 1, so the Leibniz test, I would only try that if I have an alternating series. And that should be easy to recognize. Right? If the series is alternating, then the Leibniz test is the first one I'd try, of course. If it's not alternating, that doesn't work, so no need to try. All right, so basically getting a limit that is equal to 1 is the worst thing that could happen when you try those tests, because again, that means you just wasted a lot of time and you didn't get an answer. Any more questions? Otherwise, I'd say we have some more time, so we can take a look at a couple more examples. Let's see which ones of those are nice. Yep, so second round of examples. Let's start with, maybe I'll give you 2. So again, the question is, does this converge? No need to compute the limit. Of course you can. So just because the problem statement doesn't ask for the limit, that should be a hint that the root or the ratio test might be the first thing you should consider. But it might still be easier to actually compute the limit, and of course you're free to do so. Right? If you see immediately, well, this is a geometric series, then just write that down. You're done. So first example, from 0 to infinity, 2n squared plus 1 over n factorial. And let me just write down those 2 examples I'd like you to try first. And then give me a second to address some of the questions before you start computing those. Because there have been a couple of questions I'd like to answer first for the problems we discussed earlier. First question, let's see, where do we have that? Yeah, first question concerns this problem here. You remember we applied Euler's series here to get this result. And the question was, why is it n to the power of 3 and not just n, and not just e, sorry. And the answer is, well, this formula here, we apply this with x equals 3. So this 3 here, let me color that. This 3 here, that corresponds to the value x in the formula. And that is where this to the power of 3 comes from. This is that 3 here. And that corresponds to this x here. So if you just apply that formula directly, you get e to the power of 3 from that. Another question concerns this reformulation here. So I reformulated 1 over 2 to the power of k plus 1 into that form. And of course, formally, what I have done but not written down is I first rewrote that in the form 1 to the power of k plus 1 over 2 to the power of k plus 1. And of course, I can do that because 1 to whatever power is still 1. Right? And then I can write that as 1 over 2 to the power of k plus 1. That's what I did. I just didn't mention that step. So that was this one. And also for that question, what I did here in the first step was I split up that series into 2. And of course, I have to argue why that is actually allowed. Maybe I shortened that a little. So my argument here is the following. These 2 series here each converge. And that means if I just add those 2 series, I will again get a convergent series. And the limit of that new series will be the sum of the 2 individual limits. Right? So my argument is kind of backwards. I'm saying, looking at this and the result, this here, in the end I found out the 2 series converge, so they do converge, and that means I can add them, and I will get a convergent series. And this is why this series is convergent. So the argument works its way from the result to the beginning, actually. If one of those didn't converge, I can't do that first step. Right? So it might very well be that this series is convergent, but if I split it up in the wrong way, I end up with something non-convergent. And of course, that's completely wrong. I can't do that. I can only do that because it all converges in the end. And that allows me to deduce convergence of that original series. Just to make that very clear. Yeah, that's why I can split it up. Otherwise, I couldn't. So if I wanted to prove divergence, I couldn't use that approach. First step would be wrong already. All right. And then there's a question about the exam. Is it necessary to provide any proof if the task only asks for whether a series or sequence converges or diverges? And usual answer, the exam will say that. So usually, either the question will be, does this series converge or diverge? No need to provide a justification. Then you can just say yes or no. Usually, I will say something like, does this series converge or diverge? Provide some justification for your answer. And then, of course, you are required to provide a proof or a conclusive computation to back up your answer. And just to say that very clearly, if I'm asking for a justification, then just saying yes or no will get you no credits at all, even if it's correct. All right, so I think that is almost all. Okay, one more question about the warm-up. Where do I have that? This here. So other question about the warm-up is, where does this -1 come from? The answer is that -1, let me maybe color that, comes from the fact that here we are summing up starting at n equals 1, and here we extended the sum to start from 0. So we added one summand, and of course, so that both are equal, we need to subtract that summand afterwards, and that summand is equal to 1. Right? So the case n equals 0 here, that will yield 3 to the power of 0 over 0 factorial, so that's 1. And that means if I start at 0 and then subtract 1, that's the same as starting at 1. That's where this -1 comes from. All right, now back to the examples. So you still have a few minutes to take a look at those. So let's see what you get. Sorry? Yes, that's minus. Let me clarify that. Sorry, bad handwriting. That should be better. Actually, very bad handwriting. I'm very sorry. This is supposed to be not a minus, but instead a multiplication sign. My bad. That makes it just a little easier. You can also try the version with the minus, though. Another question? Always K's. Yeah, maybe I should have written those down. So here we have a K, and let's say we start from 1. Doesn't really matter. So we are approaching the end, so maybe we'll keep it brief. Give you 30 more seconds to cast your votes, and then we'll take a quick look at the answers. All right, for the first one, this is your answers, and most of you recognize that this series is convergent. And I guess most of you applied the root test here. Sorry, the ratio test. The ratio test, of course. Usually these n factorials that are kind of a giveaway for the ratio test, right? So you want to try that first, and it should work out pretty smoothly. For the second one, you could also try the ratio test, or you could just remember that we've discussed that one already. Actually, that's an example of a geometric series, so you should even be able to get the limit of that. All right, I don't think I need to put down all the details. If you didn't get that right, just ask in the exercise session afterwards. One more question from the feedback that I'd briefly like to discuss before we end this session. You do remember we discussed the harmonic series, this one here, and I claimed it diverges. I showed you it diverges, and I hope you believe me. However, if you apply the ratio test to this one, so of course the an is 1 over n, that means an plus 1 over an is 1 over n plus 1 times n times 1, like that. And now the question said, well, obviously this expression is always less than 1. So wouldn't that mean this series converges? Why is that not true? What's the problem here? I mean, I did say that taking the limit would probably simplify things and make it easier, but it's not strictly necessary, right? Yeah? The limit approach is one, that's right. So if you take the limit, you'll get the correct answer. Not a useful answer, but still the correct answer. Right, so this for n goes to infinity. This will approach 1, so that means the test is inconclusive. But what about this argument? I mean, I did say in the beginning that we don't really need the limits, right? If you remember that. What's the catch? What do we need that we don't get here? Yes? It has to start from 0. No, it can start from 1. That's okay. It couldn't start from 0 because 1 over 0 is not defined. That's why it started from 1. Yeah? I went n by something that's n plus 1. So the denominator is always greater by 1. So that expression is always less than 1, right? No matter what the n is. The limit is 1, that's correct. But what about if I don't want to use the limit? And we usually did use the limit, but strictly speaking, there was a way that didn't use the limit. Why does that not work here? Maybe let's take a quick look at the lecture notes here. So this is the first part about the ratio test from the lecture notes. And what I said here is this expression here, I want to look at this expression, and that needs to satisfy this inequality. No limit involved. The problem here is I need that to be less or equal to some constant q, and that q needs to be less than 1, strictly less than 1. And that is what doesn't work here. Right? So I have this expression n over, maybe I don't want to use green for that. I have this expression n over n plus 1. And if I want to bound that by some constant q that is less than 1, that is not going to work. That q needs to be some universal constant. And there is no such constant, because whatever I choose, I can always find an n such that my expression is between q and 1. It will always surpass anything that is strictly less than 1 at some point. Right? So point is, there is no such q, because for large enough n, we always get q is less than n over n plus 1 is less than 1, right? So no matter what q I choose, I can always find an n that breaks this inequality. And that's why this limitless argument doesn't work. So basically, you're on the safe side if you just always use limits. And usually that works in the examples that you'll consider. There might be some examples where it's hard to get the limit, and this is actually easier to see, or maybe there's only this possibility, but I'd say that doesn't apply to all the examples that you will see in this course. Those are pretty exotic. All right, so just use the limit, you're on the safe side. I hope that did answer this question. So that was the last lecture before the holiday break, before the winter break. I hope you all have relaxing days over Christmas. I hope you have a happy new year, and I'll see you in January, or hopefully in the exercise session right away.